Hi, everybody. This is Yuzhang again. And, I'm a professor in the Department of Civil and Environmental Engineering at USF. And this is our Friday Transition Research Seminar series. And this is our last seminar in our fourth semester. And we're very glad to have Dr. Marwa Hassan with us today. And Dr. Hassan is the CETF Distinguished Professor and a Jacobs Professor of Excellence in the Department of Construction Management in the College of Engineering at Louisiana State University. And she also served as the Director of the Regional UTC Transset. And Dr. Hassan is a member of LSU Faculty Standard Executive Committee, and she also serves as a department graduate coordinator for 7 years from 2012 to 2018. And I'm serving on the graduate committee. I know that's a lot of work, even just as a committee member, but she has served as a coordinator for a long time. So Dr. Hassan's expertise is evaluation and categorization of sustainable infrastructure materials and the life cycle assessment. And, for the flyer that we send out, there's more information about Dr. Hassan, and you can see that from the slide. So I will save the time and I will give the floor to Dr. Hassan. Thank you for being here. We look forward to listening to your presentation.
Thank you so much, Dr. Zhang, for this nice introduction. I'm happy to be here. Welcome, everyone. So today I'm going to talk to you about innovative infrastructure materials. Before I do that, I would like to introduce our UTC very quickly. So as Dr. Zhang said, I'm the director of a regional UTC called Transit. Transit is a $15 million UTC that serves Region 6. It started in November 2016. And our main objective is to solve emerging transportation resiliency, sustainability, and economic challenges through the use of innovative materials and construction methods. And we focus on everything from research to implementation. We are a consortium of 11 institutions from the 5 states, Louisiana, Texas, Oklahoma, New Mexico, and Arkansas. We have 2 community colleges as part of the consortium, BRCC and NTU. I wanted to give you an overview. So we do 4 things: research, education, workforce development, and tech transfer. With respect to research, we have funded to date 139 projects, and the total funding is about $18.5 million. We were able to also generate an additional $2.1 million. We focus on collaboration a lot, meaning that 2 institutions from the consortium are working together on the project so that we can further the education and tech transfer policy. And from that perspective, we funded 37 collaborative projects. These projects resulted in 203 new technologies. From an education perspective, we host a lot of STEM events, and we generate modules and we integrate them into classes in all of the institutions of the consortium. And to date, we have hosted 91 STEM events and developed over 130 new educational modules and supported over 600 students. With respect to tech transfer, our numbers are improving every day, every year, and we have developed a webinar series and seminar series. The webinar series is quarterly, and it varies in presenting different transportation topics and challenges. We also have all the final reports from all the projects on our website available for download. We look at how many downloads we get and the number of citation, and we also look at how many presentations and publications are presented. The tech transfer mission is very important to transfer. So we have integrated it within our working process or operation mechanisms from the beginning. Before we fund any project, we try to identify what the problems are in the region, by talking to our stakeholders. And then we identify PIs that can solve these problems and we put them together. Throughout the duration of the project, we create what we call project review committees or PRCs that meet with the PIs periodically to make sure that the research is going in the right direction and it's going to be implementable. At the end of the project, we always give a 6-month implementation period where the PIs are also working with their PRCs to do the first steps towards implementation. With respect to workforce development, we also participate in a lot of events. We host our own conferences, but we participate in professional society events, and we host workshops and seminars to educate the DOT and industry on the outcomes of the research. We are very data centric, so we collect a lot of data in order to make sure that we are performing up to standard. And here are some of our performance metrics in the categories of tech transfer, education, and workforce development. And as you can see, we have trends that are going up all the time and new partners that we are creating and growing with the center for collaboration. This slide here shows some of the implementation of some of the research projects. As you can see here, those pictures are from a pavement marking implementation project. This is ultra high performance fiber reinforced concrete being constructed in New Mexico. And this is actually right in front of my office. This is our engineering building. And this is what we call bendable concrete or engineering concrete composites. And this particular mix has a funny story that I'm going to tell you as we proceed through the presentation. And we do a lot more. We have so many activities. So this slide here, these activities that we do. This picture here is showing an event that took place in PVAMU for freshman students to get them interested in transportation. This is a field implementation that happened in Dallas Airport by University of Texas Arlington, where they were installing ultra high performance fiber reinforced concrete in the runway. In here you see a Photoshop after an artificial intelligence workshop that took place in Arkansas State. This is a workshop that we held for the industry to teach them about FCCs, a Tech Fest event to get the public interested in engineering in general. And that's one of our associate directors, Dr. Samir Dusui, winning an award from ITE. Okay, so this is a quick introduction about Transit. I hope I didn't take too much time, but I just wanted you guys to know what it is. Now I'm going to talk about our effort, our research group's effort in creating innovative materials for our infrastructure. Okay, so this picture here just summarizes some of the technology that we've developed in the past. I'm not going to have the time to talk about all of them, but I just wanted to show you. This is photocatalytic pavements, and that's a new generation of pavements that integrates nano-titanium dioxide inside the mixes. It can be applied to both asphalt and concrete. And what the nano-titanium dioxide acts as is a catalyst. It breaks the water molecules in the humidity into hydroxyl radicals and superoxides. And then these unstable chemical compounds starts reacting with the pollutants in the air. So NOx becomes nitrate salts, SO2 becomes sulfate salts, and any kind of VOC that's very harmful to the environment ends being carbon dioxide. The salts are deposited on the pavement and washed by rain, which means that people can drive their cars and SUVs without having any conscious telling them that they are polluting the environment, because the road itself acts like the converter of these pollutants and purifies the air quality again. This picture here shows a project where we developed shingles that were made from recycled glass cullets to reduce the urban heat island problem. The picture at the bottom right talks about low cost and ultra high performance ECCs, and we had a lot of work done in this area. I'm actually going to be presenting this today. The next picture in the middle shows EGC, what we call engineered geopolymer composite, which is something that we created and started working on. It's the same as ECC. It's bendable or highly flexible, highly ductile, but based on geopolymer instead of cementitious matrices. And then the last two pictures here show self-healing technologies applied to both concrete pavements and asphalt pavements. And although I won't get a chance to talk about the concrete self-healing, but I'm going to give you an introduction on the asphalt self-healing towards the end of my presentation. So to get started, let's talk about ECC or bendable concrete and how it's used in sustainable materials. Okay, so concrete, we've all heard the saying, if it ain't cracked, it ain't concrete. Why is that? It's because concrete, although it's very important in our lives, it's a brittle material by nature. It's prone to cracking. It's a permeable material, which means it allows the litter substances to enter into the concrete. And that leads to a lot of deterioration mechanisms. In addition to the fact that because of its brittleness, we have to construct it with joints. And joints present another mechanism like joint faulting, joint spalling, and corner breaks. So does ECC present a solution to this? I would say yes. ECC was developed by Dr. Victor Lee from the University of Michigan about 25 years ago. The main advantages of ECC compared to concrete is that it exhibits what we call pseudostrain hardening after cracking. What does that do? That leads to an increase in load carrying capacity with a significant increase in deformation, which allows us to produce bendable concrete, as you can see in the picture right here. Okay, so what is pseudostrain hardening? The pseudostrain hardening is a behavior that allows the material to exhibit micro cracks. You can see here, there are so many cracks instead of just one, right? When we look at concrete cracking, we have one, even fiber reinforced cracking, we still have one, although the reinforcement try to bridge the gap in the crack, right? So if we look at this figure right here, I'm sorry, it compares the stress strain behavior of regular concrete, fiber reinforced concrete, and ECC. This behavior allows the material to exhibit high ductility, which is sometimes 10 to 800 times more than regular concrete. The flexural strength also is 2 to 3 times that of regular concrete. In addition, because we are getting very small cracks instead of a major crack, that makes the material more susceptible to self-healing, or what we call autogenous healing, the formation of calcium carbonate that could close the crack, which means that it's a better environment for prevention of durability-related problems, or even corrosion of the reinforcement inside the concrete. Okay, so how do we design ECC? ECC design is based on two main criteria, what we call the strength criteria and the energy criteria. The strength criteria warrants adequate fiber bridging capacity upon crack initiation, while the energy criteria guarantees the occurrence of steady-state flat crack propagation. The strength criteria requires, as you can see from the equations right here, that the maximum fiber bridging capacity, what we call sigma node, is larger than or equal to the matrix cracking strength, sigma critical. The energy criteria, on the other hand, require that the complementary energy of the fiber bridging relation, what we call JB prime, is greater than or equal to the crack tip matrix toughness J tip. If we can satisfy both criteria, then we will get the pseudostrain hardening behavior, and we will get bendable concrete. Okay, so why is that important? Why is it useful? There are many advantages and implications that would affect design if we do that. The first of which is that we can significantly reduce the thickness of the concrete structure that we're constructing. We actually have designed an ultra-thin white topping using ECC, and with regular concrete, we would have had to design the section with 5 inches. With ECC, 2 inches was more than sufficient. We can also, because it's ductile, create jointless concrete pavements, and that eliminates the need for a lot of repair, but it also reduces construction costs in terms of labor, material, and time. So overall, we are creating more resilient and durable infrastructure. So if that's the case, and if it's a nice material and it has been invented by Dr. Lee over 25 years ago, why isn't it fully implemented by now? And the limitations is really the high cost and the high environmental footprint that, that it comes with the material. So let's talk about the high cost for a second first. ECC has high cement content, which makes it very expensive. It also has what we call oil-coated polyvinyl alcohol fibers. These are very expensive, and we put 2% by volume, which increases the cost drastically. In the field, to disperse that many fiber, in addition to it being expensive, it also requires a lot of quality control. And if the fibers are not dispersed properly, then you're going to get lots of quality control issues. That's from a cost perspective. So the use of the microsilica sand, the fibers, and the fact that it has high cement content. The high cement content also affects the environmental performance because there is a lot of CO2 emissions that can be associated with that as well. So what did we do to solve these problems? In transit, we started working about solutions to make this technology implementable. So we started by looking, can we bring down the cost of ECC? We wanted to change the fibers. So can we use non-oil coated fibers, for example, because they are much more cheaper than oil coated? And we wanted to reduce the fiber content. Instead of using 2%, go to 1.5 or 1.75 volume fraction. We also looked at the microsilica sand and tried to replace it with locally available material. In the region 6, river sand is available and it can be used instead of the microsilica sand. We also looked at reducing the cement content by using other SCMs, and we experimented with fly ash, as well as other recycled content. We also looked at putting waste materials into the ECC mixes like chrome rubber. We were able to successfully create low-cost ECC that was about 30% of the cost of the ECC that was developed by Dr. Victor Lee. And we looked further, so if this is successful, what else can we do? We started experimenting with other types of ash other than fly ash, and we experimented with processed bagasse ash. We used that as a replacement for both cement and sand. Actually, the ECC modified non-oil coated bagasse ash is a patent that we just got approved last month. So we can produce any ECC with non-oil coated fiber that has bagasse ash in it. We also looked at the high-end spectrum of ECC. If we can produce low-cost ECCs, can we also create ultra-high performance ECCs? And we developed mixes for ultra-high performance ECCs, and I'm going to show you an overview of that. While doing all of this work, we were always looking at the pavement performance and its fatigue life. So we built lots of modeling using finite element analysis to simulate the performance. Okay, so I don't have time to go into details with everything that I've just talked about, but I'm going to give you snapshots of some of the results that we've gotten with some of these mixes. Let's start with the low-cost ECC that has fly ash and chrome rubber. And this slide just shows the compressive strength of the mixes. As I said, we were able to develop the mixes successfully. As you can see here, the ECC has different contents of fly ash, and it also has coarse sand and fine sand. We found that the ECC with the coarse sand exhibited higher compressive strength as compared to the ECC with the fine sand. This was the case for both cases, the regular as well as the chrome rubber ECC. As you can see, the compressive strength was drastically reduced by using the chrome rubber, which is expected due to poor bonding between the cementitious matrix and the low stiffness of the chrome rubber. This slide shows the tensile strength of the regular ECC and the chrome rubber ECC. And although we saw that the same effects in terms of tensile and flexural strength, it's notable to say that the tensile ductility was improved drastically when we used 20% chrome rubber ECC. So to conclude this part, the main finding that we found was that PVA ECC materials with low fiber content 1.5% or 1.75%, and local ingredients is doable. We can produce ECC with these mixes. And increasing the content of cement replacement with fly ash increased the ductility of the composites, but it reduced the compressive, tensile, and flexural strength. Crumb rubber also had a significant reduction in compressive and flexural strength, yet the deformation capacity and strain were drastically improved. This slide here shows the best mix that we were able to develop in terms of economics and performance. We call it M3 1.5%. And you can see here the properties of it. It had a compressive strength 25% better than regular concrete, flexural strength 113% better than regular concrete, a tensile strength of 20% better than regular concrete, tensile strain capacity of more than 31,000 better than concrete. We actually use this mix in an accelerated loaded testing study that is currently going on in Louisiana. The second type of ECC that I want to introduce you to is the Bagasse ECC. So let me first tell you what Bagasse Ecc is. Bagasse is a byproduct of the sugar production. We are producing about 0.76 billion tons per year globally. It's currently used as a source of energy in sugar mills, so they burn it in order to get heat for their facilities. But once they do, that's what you see in the picture, heaps of mountains of ash, and it's a disposable problem and a potential fire hazard. They don't know what to do with it. So, I'm sorry, I jumped too much. Okay. So our objective in this study was to implement sugarcane bagasse ash as two things: sand replacement, to replace the microsilica sand, and cement replacement so that we can reduce the cement content and bring the cost down further. Then we wanted to see how will that impact the mechanistic performance of the concrete. Okay, so let me just talk a little bit about how to process the bagasse ash. What you're seeing in the first picture right here is what we get from the mills. It's that heap that is present. We just go and take it. Then we dry it at 65 degrees to get rid of the humidity because it's sitting there. And then we just sieve it to get rid of the coarse particles. Once you do those two steps, which is very minimal processing, we get what we call raw sugarcane bagasse ash, and this is what we use as sand replacement, as is, no more processing needed. If we further process it by burning it at 450 degrees Celsius for 3 hours, then grind it at 300 RPM for 35 minutes, we get what we call post-processed bagasse ash, and this is what we use as cement replacement. We have done a lot of work in terms of identifying the strength activity index and the chemical composition of the bagasse ash to see that it's suitable for placing in the cement. This is just a snapshot, some SEM pictures for the sugarcane bagasse ash and the post-processed bagasse ash. As you can see, the sugarcane bagasse ash has some unburned fibers, irregular porous structure, and charismatic particles. When you look at the post-processed bagasse ash, you still have the charismatic particles and the porous particles, but you no longer have the unburned fibrous particles. So the unburned fibrous particles is what we get rid by sieving. And the remaining particles are pretty much crystalline silica and amorphous silica, which indicates that we have an activity index, so it can be used as cement replacement. This is just a snapshot again of results. So the compressive strength, as you can see from these figures, the use of sugarcane bagasse ash as sand replacement produced minimal effect on the compressive strength. It works pretty well there, but it did reduce the compressive strength when we used it as cement replacement. Although when we did the test to identify the strength activity index, and when we did the SEM, we saw amorphous silica, which indicates that there is pozzolanic activities. We believe that the early strength is going to be lower, but as you leave it over time, the strength will increase. So we expect these numbers to increase over time. This is a snapshot of the tensile properties. And for the post-processed bagasse ash, we can see that the mix with 40% replacement had the highest tensile strength, with a small increase over the ECC control mix that didn't have any. As for the tensile strain capacity, we can see that replacing the cement with post-processed bagasse ash improved the tensile strain capacity. The best performing mix, as you can see, was the one with 50% cement replacement. So here are some main conclusions that we found. Raw bagasse ash met the minimum pozzolanic component requirements for Class T pozzolans, and post-processed ash met the SAI requirements to be utilized as an SEM, which is great. In general, the compressive strength decreased with an increase in the bagasse ash, in the raw bagasse ash and the post-processed bagasse ash in the mix. We saw an improvement in the tensile ductility of 311% compared to the control mix. The tensile strengths of the raw bagasse ash admixture were higher than that of the control mix. An improvement of up to 85% was seen in comparison to control when observed with 50% cement replacement of bagasse ash or processed bagasse ash. So the bigger conclusion is use of raw bagasse ash as sand replacement and use of post-processed bagasse ash as cement replacement in ECCs is feasible, and it's highly recommended, and it's also making the technology much more cost effective. Okay. The last ECC that I'm going to introduce is ultra high performance ECC. I'm sorry, someone is getting, I'm getting all of these messages. Okay, so ultra high performance ECCs. What is the definition of ultra high performance ECC? It's that can have an ultra high performance compressive strength of more than 120 megapascal. Here, this table also summarizes the properties that we are expected to get. So we want a compressive strength of more than 120 megapascal, a tensile strength of 8 to 18 megapascal, a tensile strain of 2 or more, or 2 to 8% capacity, tensile strain capacity, and small crack widths, of course, under than 100 micrometers. Okay. So why would we go for designing ultra high performance ECCs? Or why go after this research? If we look for ultra high performance materials in general, and specifically ECC, we'll see that they are expensive and impractical to implement. The leader of the research in this area is coming from Northwestern, Dr. Shah, and we are doing a lot of work in this area as well. But before we started our work, this was the best performance that we found from the literature. So we're looking at the use of ultra-high molecular weight polyethylene fibers at 2% volume fraction and very expensive SCMs like silica fumes. So again, to bring this back to practice and to actual implementation, we wanted to see if we can reduce the cost of ultra-high performance ECC and still design it successfully. So we wanted to again replace microsilica sand with natural sand, reduce the fiber content as much as possible, and get rid of the expensive SCMs like the silica fumes. Okay, and we did so many trials. Like I'm showing you the successful part of the matrix after 8 months of work. But this slide here shows 4 mixes that were very successful. They all exhibited a compressive strength higher than 120 megapascal with low fiber content without affecting the ECC performance. So as you can see here, if you look, we have 1.5% and 2% fiber content. We have no silica fumes. The best performing one right here has no silica fumes and has 1.5% fiber content. Based on tensile properties, and as you can see here, we see high ductility. We are getting the pseudostrain hardening effect that we are looking for. And the mix with 25% fly ash and 1.5% fiber content was the best performance in the tensile test. And it had the highest tensile strain capacity. This is the flexural results as well. We can see that the mix with the 25% fly ash and 2% fiber was the best performer, and it experienced the highest deflection capacity. So to conclude, we were able to design mixes that ranged between 115 to 133 megapascals. All the composites presented here had ECC-like ductility with more than 2% tensile strain capacity. And the flexural strength of the composite ranged from 20.9 to 24.4, which is 4 to 5 times that of regular concrete. So we were able to successfully design ultra-high performance ECC with local ingredients and at a much lower cost. We are working right now on 3D printing of ultra-high performance ECC, which is not part of this presentation. Oh, this mix, I just wanted to give you the properties of this mix. It does not incorporate any silica fumes, and it has a relatively low fiber content. And here are the properties. As you can see, it's very successful and very useful. Okay, so we have done a lot of attempts towards implementation, and here are some of the field implementation that we had done at LSU. This shows how we're working with facility services around campus. In LSU, we have 100-year-old trees with very deep roots that are breaking the concrete sidewalks all the time. So we suggested to facility services to try our mixes. That's the low-cost ECC. And as you can see here, they constructed them. They have been in operation right now for about 2.5 years. We're not seeing a single crack. They are so easy to use, and the people in facility services love them to the degree that they asked us to periodically prepare mixes for them. They use them for potholing around campus. Whenever they see a crack, they fill it with ECC now, which is kind of funny. This is the placement of ECC as pavement. And this part itself has a funny story because they wanted to repair that pavement with the low-cost ECC. And we gave the contractor the M3 1.5 mix that I just talked to you guys about. But the contractor made a mistake and he reduced the cement content even further, which we ended up with a mix that has a very low compressive strength. It's comparable to flexible pavements more than concrete pavements. We expected this to crack within a month of traffic because that road has a lot of bus traffic on it. It didn't. It has been in operation for 1.5 years, which is telling us that this type of material can even be an alternative to flexible pavements given the proper research. It's just an interesting fact that I always find fascinating. A third implementation study is an actual full-scale accelerated loaded testing that we are conducting right now. It's a jointless white topping overlay that is placed on an asphalt surface. It's fully instrumented with load cell, strain gauges, etc. And if you look here, this is the general overlay of the test. What we have is 2.5-inch ECC with a transition, then 4-inch ECC, then the control section, which is 4-inch concrete. 60 feet, 55 feet, and 60 feet in length. This is a picture of the instrumentation that were used in the project. And in here, you can see pictures from the construction on the day that we actually did it. I want to give credit to a lot of the local industry that helped us in the construction, Lemoyne and Icon Construction and Quality Concrete. And we are currently testing these sections to failure. So far, we are seeing very small cracks and it's not failing. We should be able to submit a paper on this in the next TRB. Okay, so the second sustainable material that I want to introduce is engineered geopolymer composites, or what we call EGCs. This work is a collaboration between LSU and Texas A&M. Dr. Miladin Radovic and Dr. Svetlana from the Material Science Department. Okay, if you allow me just to get a sip of water. All right, so as I said before, EGCs are ECC that are using geopolymer instead of cementitious matrix. Why would we do that? Because geopolymer binders have so many advantages. They have faster strength development. They are more resistant to acid attacks and fires. They also prevent the corrosion of the steel reinforcement, and using geopolymer will reduce the CO2 emissions by 44 to 64%, which makes it environmentally friendly. Last but not least, also the geopolymer matrix will have a lower J-tip, which the same comparable strengths, which lends itself to the pseudostrain hardening behavior that we are trying to achieve with design of ECCs. Okay, so what is a geopolymer? As you all know, geopolymers are made by mixing what we call geopolymer precursor with an activator solution. Geopolymer precursors can be many things, from waste materials like fly ash and slag to natural occurring materials like kaolinite, like metakaline, etc. The activator solutions are sodium hydroxide or potassium hydroxide. It's an alkaline silicate solution that can increase the silica aluminum ratio. So what was our objective here? We wanted to develop EGCs that are based on either metakaline or a hybrid metakaline fly ash base. And to achieve this, we changed the binder composition, aggregate type, and fiber type and content that was used. Okay, so this slide shows, can you guys see the slide well? It's not showing properly here. Yes?
Yes. Yes.
Okay. So this slide shows the ingredients that we experimented with from a geopolymer precursor perspective. As I said, we tested metakaline and a hybrid metakaline fly ash combination. From an activator solution perspective, we tested potassium hydroxide with silicon dioxide and sodium hydroxide. And then we experimented with river sand and microsilica sand. And then for fibers, we had non-oil coated PVA fibers and ultra-high molecular polyethylene fiber. This schematic shows the production method of the geopolymer or the EGC. And we start first by dissolving the activator solution into DI water and mixing it for 24 hours. At first it's cloudy. By the end of the 24 hours, you see that it became clear. Once it becomes clear, then we mix it with the geopolymer precursor metakaline or the metakaline fly ash combination, and that gives us the pure geopolymer. Then we add the sand, whether it's river sand or microsilica sand. That gives us the geopolymer mortar, and then it's placed in mold and left to cure for 7 days in sealed conditions. After that, you can start loading it after 28 days. So stripping, we usually strip the forms after 7 days, and we test it after 21 days instead of 28 in the case of regular concrete. Okay, and these are the tests that we experimented with. So we tested setting time, compressive strength, uniaxial test, and flexural test. Again, a snapshot of the results. This is the 28-day metakaline uniaxial tensile test. As you can see, all specimens showed a high ductility and pseudostrain hardening behavior. The specimen with the microsilica sand presented the best tensile performance by exhibiting a greater tensile strength and a tensile strain capacity. This is the 21-day uniaxial tensile strength for metakaline with high molecular weight polyethylene fibers instead of the PVA fibers. And again, all of the mixes showed high ductility. The highest tensile strength was achieved with the 1.5% microsilica sand, and highest tensile strain capacity was achieved with a sample of 1% river sand. This is the sad part, and we're still working on modifications, but when we tested the hybrid metakaline fly ash combination, we were not able to get the pseudostrain hardening behavior that we were hoping for, so these mixes cannot be classified as EGCs. So, quick conclusions. The tensile pseudostrain hardening behavior of the EGCs was superior to the made by polyethylene fibers is superior to the PVA one. The PVA specimens consists of from microsilica sand had a superior tensile performance when comparing to the river sand one. The opposite is observed in the polyethylene specimens in terms of ductility. We were not able to produce metakaline fly ash-based materials as they did not exhibit the pseudostrain behavior that we were looking for. Okay, that ends my talk about ECC, and now I'm going to talk about self-rejuvenating asphalt. So we're diverting from concrete to asphalt completely, but that way I'm giving you a perspective of both. Okay. So we've done a lot of work in terms of self-healing, different mechanisms for the self-healing. I'm here going to present two of them, self-healing microcapsules and sodium alginate fibers. We'll start with the microcapsules. So the idea behind self-healing is that you put some kind of a healing agent or rejuvenating agent in the case of asphalt inside the matrix that you're trying to heal. As you can see in the picture, as the crack propagates, it breaks the shell wall and releasing the healing agent so that it can close the crack. So it's very similar to a human body. When you get a cut, the white blood cells would flow into the bloodstream and then block the flow of blood, and then your skin starts to heal. So this is biomimicry of the self-healing process that occurs in a human body. We tried to implement that on the asphalt mix. So we created double-walled capsules that were made of urea formaldehyde and polyurethane. The healing agent inside is a rejuvenator, and we were looking for something to reverse the oxidation process or the aging of the binder by supplying oils and maltines to the binder. So we tested two core materials, bio-based, which was just sunflower oil, the same oil that we use for cooking. And then we used another bio-base that is synthetic. It's called Rejuve8 for the sake of the research. We made the capsules in the lab. As you can see, these are some of the characterization pictures. We are able to control the properties of the capsules by controlling the process parameters. So we control the agitation rate, the diameter, the shell thickness, etc. And you can see that we characterized what we were looking for. Also, we use double walls to make sure that the capsules are strong enough to withstand the mixing and placing construction processes of asphalt mixes. Okay, so in terms of testing, we prepared the HMA mixtures, placed them into beams, rectangular beams, tested the beam 3-point bending to induce cracks, and then left it to heal, and then looked for the healing efficiency and the stiffness recovery. So you can see here, that's the 3-point bending test setup. And we measured the healing process after 6 days. We left the specimens in room temperature and at high temperature. And we looked at the cracks using a light microscope after, after 1 day, 3 days, 6 days. We calculated the healing efficiency according to this equation. This is just a sample of the results. All the mixes, the crack, and then at day 6, they are almost 100% healed. This is the stiffness recovery results, and as you can see here, this specimen, which is the sunflower oil specimen, exhibited the highest stiffness recovery. Another mechanism that we developed in order to encapsulate the rejuvenator product or the healing product is sodium alginate fibers. You can see the sodium alginate fibers right here in the pictures. Why sodium alginate? It's an inexpensive material. It's organic and non-toxic, environmentally friendly. It degrades over time. So when it degrades, then it's going to slowly release the rejuvenator, reversing the aging process by itself. Also, it's an elastic material, so it might even improve the mechanistic behavior of the asphalt mix. So in here, there is a short video that just shows you how we developed these fibers. If you look at it, we developed a fiber synthesis procedure that is currently under review to be patented to prepare the sodium alginate fibers containing the rejuvenator. And I don't want the video to keep on going while I'm talking, so I'll just continue. So it uses, as you saw, a wet spinning process. The core material was, in that case, a green bioproduct, which is the same one I talked about a minute ago, Rejuve 8. And the bath right here is just a calcium chloride bath at a molarity of 0.6. And as you can see, the fibers are formed and then they are left to dry before we cut them and put them in the binder. All right, so here are some of the results. This is results from the LWT test. And as you can see, so this is the asphalt with nothing. This is with 5% trap. And then this is with 5% trap and the sodium alginate fibers. As you can see, of course, we expected the rotting tabs to drop when the wrap is added, but it did not increase, which means that the fibers are doing what they're supposed to do. We also did Stb testing. And as you can see here, adding the sodium alginate fiber improved the mix cracking resistance because it's higher than with the wrap content. We also looked at the low temperature cracking resistance by running TSRST. And as you can see, the temperature and the failure load, the temperature decreased and the failure load increased, which means that it's improving the susceptibility to low temperature cracking. I'm sorry. So in conclusion, sodium alginate fibers reduced the stiffening effect obtained with recycled materials, which suggested some rejuvenating effects taking place. The SCB test results showed that the addition of sodium alginate improved the performance against fatigue cracking. And the addition of the developed fibers improved the low temperature performance of the mixes, which suggests that it has better performance in terms of low temperature cracking. And with that, I end my presentation. I've given you too much information. I apologize for that in advance, but I just wanted people to have more breadth and then they can ask questions. We can go in depth as much as you want.
Thank you, Dr. Hassan, for your really enlightening presentation and a lot of information.
You're very welcome.
So let's see if we have any questions from the audience. We have attendees both online and also in the room on campus. So let's see if there's any question.
So,
maybe I can start with my question.
Sure.
Dr. Hassan, I'm kind of curious about the performance of the like the low-cost ECC and also the shortcutting Bagasse fiber ECC. And you mentioned about the in your slides you presented that the significant improvement in terms of strength, in compressive strength and tensile strength. I'm curious about the fatigue performance of these kind of materials, particularly when you put them in the pavement, and fatigue performance is one of the critical performances.
That's an excellent question, and I have an amazing answer for it. This was one of the things that we were designing for from the beginning. So in terms of fatigue, we are trying to determine the fatigue life in the accelerated loaded testing facility. Remember the ALF study that I showed you?
Right.
So right now we are not expecting it like we're not expecting it to fail. We're expecting it to pass the crosshold without failing at all. One of my PhD students, Dr. Hassan Orvand, actually built a finite element model to predict the fatigue life, and it has exceeded 50,000 cycles.
Okay.
And that is, I'm talking here about the low-cost ECC, the M3 1.5 mix, which is the most economical mix. It's not even like the Bagasse performance was better than this one. We are currently working with the Deputy Secretary of Transportation in Louisiana to implement 3 mixes: the M3 1.5, the Bagasse Ash mix, and one of the ultra-high performance ECC mixes in a low-volume road in Baton Rouge, which it will be exposed to real traffic, because the modeling and what we got from the ALF is suggesting that it has a very good fatigue life.
And in that low volume load, these materials are used as like a white topping overlay or like.
Currently, the road is deteriorating asphalt pavement. We are milling 2 inches of the road and putting an overlay. Well, we'll call it ultra thin white topping since it's concrete. But so the whole road is being repaired with an asphalt overlay, except for 3 sections of 120 feet each, where we're going to put each of these materials in it. So we're going to be comparing the performance against the asphalt pavement performance.
That is interesting. So
I'm excited about this. It's harder than it
yeah, I will be very curious about the results, about the performance, and for these kind of new materials.
I would recommend, if you're interested, to look at the dissertation coming out from Hassan Norvand. It just got published because he defended 3 months ago, but it also it shows all of these results, but it also starts developing design equations of if we actually want to use ECC for pavement, how would that change the pavement design process? It's mainly designing for fatigue.
Yeah, I will look into that. Now, you mentioned that the low cost ECC. So I'm also curious about how low the cost will become.
Yes. Okay. So as I said, it's about 30% the cost of Dr. Lee's mixes, and we have done a cost analysis study to compare it with regular concrete. Right. I'm not taking into consideration the removal of the joints and the labor savings. I'm not, but just because of the reduction in thickness, the cost of the ECC is about 1.2 to 1.25 that of regular concrete right now with the low cost ECC. When you add to it the savings that you would get in labor cost and construction cost, it'll be very competitive actually.
Okay, so you mean in terms of the application in the field from the whole cost perspective, including have you considered like a life cycle cost analysis?
Yes, yeah, we have done schematics. I haven't published these results. Let me say, I think from a life cycle cost perspective, if you look at the environmental effects as well as the costs saving due to repair, maintenance, and construction, it's going to be much more competitive to concrete. But I'm planning to publish a full-scale hybrid LCA based on that.
Right. Thank you. Now,
you are very welcome. Thank you for your questions.
We have a question in the chat. I think some of the questions
sure.
Have already been answered. So it says, I think it's, the question is from student, actually visiting scholar, Chen Cui. She says that thank you for your presentation. My question is, are there any low-use ECC besides the LSU campus? And so I think you have kind of mentioned that you have some test section on the low volume load. And how is the long time performance on the busy traffic loading in real engineering compared with cement, concrete, or asphalt pavement? And by the way, was a full-scale test done at the LSU campus?
No, okay. I'll try to answer. If I miss part, let me know because you asked so many questions. So the accelerated loading testing is not taking place at LSU. The AL facility is part of the Louisiana Department of Transportation and Development, and it's called LTRC, and they have a pavement testing facility fully instrumented. So that's where we constructed, and they are the ones who are currently doing the testing to failure. I want to credit Dr. Tyson Robno and everybody else at the LTRC pavement testing facility for that. As far as what's going to happen over time, based on all the results we have so far, I think it's going to perform better than concrete. The thing that I want to say to a lot of audience now that we're talking at a national level is we want other states to be interested in doing field studies. The more field studies that are going to be performed, the better results we're going to get, right?
Right.
So I'm happy if anybody wants to reach out if they are interested in doing any kind of field study in their state. That would be great. We'd be very excited. I know that Virginia is interested in doing some of that work already. One of my colleagues, Dr. Gabriel Arce, who has done a lot of this work, is actually going to be leaving LSU soon and joining VTRC. So I'm sure that we're going to be seeing field studies in Virginia just because of that.
Definitely the support from the government, like from the state DOT or even from the city government agencies, will be a big help in promoting and in putting this kind of new technology into use. Now, let's see if there's any question from the audience. If not, I have another question regarding the self-healing asphalt.
Sure.
Now, I'm thinking about the mechanism of the self-healing. So will those kind of self-healing phenomenon occur when the asphalt mixture experience shear deformation instead of cracking? So those kind of rejuvenated materials, will they be released when the mixture experiences shear deformation instead of cracking?
Well, so there are two ways. If we're talking about the sodium alginate, not the microcapsules for a second. Okay, so the sodium alginate has two mechanisms. The first mechanism is that you have enough force, whether it's coming from shear deformation or actual cracking. You have to reach a threshold force, which we designed for, that would actually break the surface of the encapsulation, in that case the fiber, for the rejuvenator to come out. But the other mechanism is that the sodium alginate itself is biodegradable, so that's why it's good for reversing the aging. So over time, as the asphalt ages, the material itself will biodegrade, releasing it into the depths of the pavement. So you don't even have to have a crack or a load for that mechanism to take place. That doesn't happen with microcapsules. It's only the sodium alginate fibers.
But will that negatively affect the stiffness of the mix?
The biodegradation will not take place before 10 to 15 years from the service life, which actually works very well for asphalt binders. Right now, we are trying to put the rejuvenators, and we usually put them on the surface. It doesn't go into the depths of the pavement. So most of the time, we don't even see any rejuvenation effects. But since this is going to be embedded within the depths of the pavement, we should be seeing reversing of the oxidation process throughout the depths of the pavement.
Thank you.
Thank you so much for your questions. I'm really enjoying them.
Thank you for the detailed answers. And well, we are kind of running over the time, but let's see if there's any questions from the audience. If not, I think if you have a question later, you can still reach Dr. Hassan. Through email or through maybe even through phone call.
Please do, guys. If you have any questions or thoughts, or you just want to discuss something that relates to your research, if you're a student, I'm very happy to help.
Yeah. So, Dr. Hassan, your presentation will be posted online later, so that will attract probably more audience. And this morning I was having a meeting with an engineer in downtown Tampa actually. I mentioned that your presentation, and he is very interested in. So I'm gonna send him the link to this presentation later.
Excellent. Thank you.
With that, if there's no further question, please join me in thanking Dr. Hassan for your excellent presentations and in a virtual round of applause.
Thank you so much. Thank you so much, guys. I wish I was there. Hopefully, we'll be able to travel again everywhere soon.
Yeah, we hope we can have you here later in the future when the pandemic is over.
I'm looking forward to that.
Thank you.
Bye.
Thank you, Dr. Hassan. Bye-bye. Happy holidays.
Happy holidays to you guys.
So this will be the last presentation, last seminar in this semester. So our seminar series will continue next semester in the spring.
Yes.
Okay.
Thank you, doctor. Thank you very much.
Bye.
Thank you, Dr. Marwa.
Thank you, guys. Bye.